Hi, today we are going to go over a couple examples from Chapter 7 on looking at energy released from an electron that has jumped from a standard ground state up to an excited state, or it's fallen from an excited state back to a ground state. This is looking at Bohr's model of the atom. If we talk about energy shells or rings, that's what's being referred to here. So when we look at an atom and a compound, our first example here is when copper chloride, and this is Cu+1, so this is copper 1, as heated to 1200 degrees Celsius. The compound emits blue light with a wavelength of 450 nanometers. What is the quantum energy emitted? Okay, so first thing to note is that it gives us a wavelength here in nanometers, and we need to convert that into meters. So 450 nanometers. 450 nanometers times 10 to the negative 9th is going to put that in meters, is going to give us an answer then that's in meters, because again, nanometers is 1 times, to go from nanometers to meters, 1 meter equals 1 times 10 to the minus 9th nanometers. Okay, so in this case, then we're going straight over. That's going to give us an answer then in meters. However, 450 times 10 to the 9th, it's not good standard notation for scientific notation. So if I want to move this and change it to 4.50 nanometers, we're going to times it, nanometers, we're going to times it by 10 to the negative 7th, and that's going to give us our answer again in meters. Okay, so we have then that equivalent that we can put in. All right, so what equation should we use? Well, there are several given to you on the official AP sheet, and if we look, we've gotten, I say several, but there's really only 2. We have E equals hv, which is h is Planck's constant, and v in this case is the frequency, and we have c, which is the speed of light, is equal to the wavelength times the frequency. Okay, so those are the 2 items we have. You're going to notice that the constants are all listed here, even for the charge of a single electron in coulombs. Planck's constant and the speed of light is listed there. Okay, so when we then begin, we're going to use the equation from your notes. E equals hc divided by wavelength. Okay, so how did we get that? Well, it is just a combination of these 2. Since both of them have frequency in common, we can rearrange and combine these 2 equations to give us this version. Okay, so when we go to plug in values, then the first one is Planck's constant, which again is 6.626 times 10 to the negative 34th. It's in joules seconds, and then that is going to be multiplied by c, the speed of light, which is 3.00 times 10 to the 8th meters per second. All right, so that is then over the wavelength. What's the wavelength? Well, the wavelength was 450 nanometers. Again, the units here in the equation for the speed of light are in meters, so we've got to use a value that's in meters. You could plug in either of these, but since I took the time to adjust this one, we'll go ahead and use it. 4.50 times 10 to the negative 7th meters. Okay, and our meters cross cancel. Our seconds actually cross cancel, and the only thing we have left is joules of energy. Multiplied out and rounded, we're going to end up with 4.4 times 10 to the negative 19th joules of energy. Okay, and that completes the first example problem. Okay, our second example problem is to determine the color of light that's emitted when an electron falls from the n equals 5 position to the n equals 2 position. Okay, so we know when an excited electron falls to its original location, it's going to emit a photon of light. And the further it falls, the more energy has to be released. The more energy released changes then the color of light that we see. You'll remember from the electromagnetic spectrum, which is the first section of notes here, we go from visible light spectrum. We can see things in light energy, starting with the red is the lowest energy wavelength, the lowest energy that's emitted, and it's going to have the greatest wavelength, and it's going to have the lowest frequency and amplitude of waves. Next, and we follow the good old acronym ROY GBIV. So it goes red, orange, yellow, green, blue, indigo, and violet light for the visible electromagnetic spectrum and wavelengths. I'm going to tell you that the AP exam loves to not provide you with that electromagnetic spectrum image and ask you questions about what is going to be high energy versus low energy, high wavelength versus low wavelength, high frequency versus low frequency. So you will need to memorize the electromagnetic spectrum going from radio waves all the way up to gamma rays. And if you notice, there is somewhat of a pattern to the exponents, and then you will need to know kind of a roundabout general benchmark value for each of the visible colors of light. All right, so here is our problem, and we need to look at an energy change. The change is going to be equal to the energy at the final state. In this case, the final state is when it's gone to n equals 2 minus the energy at the initial state. Okay, so you will have noticed that in your notes you had an equation that looks like delta E equals negative 2.178 times 10 to the negative 18th joules of energy, and then it's got a handout that says, or an equation that follows, it says 1 over n final minus 1 squared over n squared initial. Okay, so that is the equation in the notes. This is also simply written as E equals negative 2.178 times 10 to the negative 18th joules times Z squared over N squared, where N squared is the energy level. It is the principal energy level. Otherwise, rings on a Bohr model. And Z is what's referred to as the nuclear charge. Now, you're going to notice that really most of these problems where we're being asked is all dealing with hydrogen, and that's because the situation gets more complicated with larger numbers of protons. So as a result, most of these problems are going to have 1 on the top because hydrogen has 1 proton, positive charge, therefore a 1 for the nuclear charge. Okay, so, but that's what z squared represents. And if we go ahead then and plug in, we can do this. And I'm going to break it down and do 2 separate instead of leaving this all together. I like to go ahead and show them separate, but of course you can combine it. So E for the initial is equal to negative 2.178 times 10 to the negative 18th joules times an initial state. It's falling from n equals 5 to n equals 2. Okay, well, what was its initial state? Well, initially, it actually began at a position that was its ground state. Okay, so this is asking how much will be emitted. And in this case, then, we're going to do that. We have a total of the initial state is going to be this, and our final state was here. Yes, that's how much would be emitted if it actually fell. But again, we're going to go with what was its initial state, what is its final state. So when we do the z charge, again, z is just going to be 1 squared, which is still just 1. And we're going to have our n equals 2 positions squared. That's going to give a value of negative 5.445 times 10 to the negative 19 joules. Okay, the E final state is negative 2.178 times 10 to the negative 18th joules. Again, the Z state here is still just 1 squared. Over in this case, the final state was its jumped excited position of 5. So 5 squared, and that's going to give us negative 8.712 times 10 to the negative 20 joules. Okay, so the change, therefore, is going to now be delta E is equal to the final state minus the initial. So we've got negative 8.712 times 10 to the negative 20 joules minus our initial state, which is also a negative value, 5.445 times 10 to the minus 19 joules. That's going to give us then a final answer of 4.569 times 10 to the minus 19 joules of energy will be released when it falls from N5 to N2. It would have required the same amount of energy to jump up to that location. Okay, so the question, though, didn't ask for energy. If we go back up, it says determine the color emitted when it does this. Okay, so we know how much the energy is. How do we relate that to the color of the light? Well, again, we're going to go back to our combined original equation that we used in our previous example, HC versus the HC over divided by the wavelength. And that basically means if I want to check and solve for wavelength, wavelength rearrange is going to give me HC over E, and in this case it's the energy of the photon. Okay, so the energy of my photon then is going to be placed here. What's the energy of the photon? The energy of the photon was this value that we just solved for. So that energy of that wavelength of light. Okay, so I'm going to go ahead now and plug in and solve. So Planck's constant is once again 6.626 times 10 to the negative 34 joules second times the speed of light, which is 2.998 times 10 to the 8th meters per second, or meters second to the -1. Okay, notice that now we're using 2.998 instead of 3.0 like I used in the other example problem, and that's because this is the actual value given on your AP reference sheet, but many times in an individual problem this gets rounded to 3.0. Okay, so that's where the difference is coming from. This just gives us more significant figures. All right, so as we continue then, that is going to be divided by the energy of the photon, which was the 4.569 times 10 to the negative 19th joules. And we can see we can start to cross cancel out units. Seconds to the -1 and seconds here. We're left with just meters. And multiplied and divided out, we end up with 4.35 times 10 to the -7th, and that is meters. Okay, then I go to the electromagnetic spectrum. So check electromagnetic spectrum chart. And I see that that wavelength would fall in the range of, looks like it's probably violet or indigo light. And then that's my actual final answer. Okay, hope this gives you a better idea at how to complete those problems from chapter 7, the first couple of assignments in Mastering Chemistry. Okay, have a good day.